If you had looked up at the sky about 4 billion years ago, the moon wouldn't be this polite, glowing silver disk that we see today.
Oh, not at all. It would have been a terrifying, blinding wall of magma taking up a massive portion of the sky,
Right, and it would be driving these incredible, like 500-foot tall tsunamis across a literally molten Earth every 5 hours.
which is just a staggering image to try and picture.
It really is. I mean, the moon is the most familiar, constant companion we have, right? It's this glowing beacon humanity has stared at for millennia.
Yeah, and it's still the only other celestial body human beings have ever set foot on.
Exactly. And yet, for something so incredibly close, it is holding on to secrets that we are, really only just beginning to unravel today.
Really are. The framework we usually apply to the moon is, well, we think of it as a lifeless rock, just a static satellite floating in the void.
Right, but you might look at the moon every single night, and tonight you are going to see it entirely differently.
Because the material we are analyzing today frames it entirely differently. It's a time capsule.
Exactly. The mission of this deep dive is to synthesize a massive stack of sources covering everything from ancient historical anthropology to literal 2025 and 2026 breakthrough scientific studies.
Studies in astrophysics, geochemistry, you name it.
Yeah, we are going to uncover the mechanics of the moon's violently chaotic origins and its invisible ironclad grip on Earth's habitability.
And of course, those newly solved mysteries hidden within the Apollo moon rocks that literally just upended 50 years of planetary science.
Okay, so let's unpack this, because before we get to the mind-bending new science about transient atmospheres and magnetic anomalies, we really need to establish the physical realities of the system.
That makes sense. We have to know what we're looking at first.
Right. I want to skip past the high school textbook definitions and look at the actual orbital mechanics. We know it's our only natural satellite, right?
Yes, sitting at an average distance of roughly 238,855 miles.
But the scale of that empty space is something that often gets, glossed over. You can actually fit all 30 Earth-sized planets within that gap.
Wow, yeah, when you put it like that, it's a massive amount of empty space.
It is. Yet despite that vast distance, the gravitational tether between our two bodies dictates this highly complex dance.
And the mechanics of that gravitational tether are precisely where things get interesting. We often say the moon orbits the Earth, but physically speaking, that's not exactly true.
Wait, really?
Yeah, well, the Earth and the moon actually orbit a shared center of mass. It's called a barycenter.
Okay, a barycenter. How does that work?
So because Earth is about 81 times more massive than the moon, that barycenter resides about 1,000 miles beneath Earth's surface.
Oh, I see. So the Earth is still kind of wobbling around that internal point.
Exactly. And as the moon navigates this orbit, it operates on two distinct cycles. First, there is the sidereal month.
Which takes about 27.3 days, right?
Correct. That is the time it takes the moon to complete one full 360-degree orbit relative to the fixed background stars.
But that's not the cycle humanity has tracked for thousands of years. We track the synodic month, the phase cycle from one full moon to the next.
Right, which takes 29.5 days.
Yeah.
And the mechanism driving that discrepancy is purely geometric.
Because the Earth is moving too, right?
Precisely. While the moon is physically traveling around the Earth is simultaneously dragging the moon along its own orbit around the sun.
So by the time the moon completes its 27.3-day loop, the Earth has moved millions of miles further down its solar orbital path.
Right, so the angle of incoming sunlight has changed. The moon has to travel an additional 2.5 days, orbiting just a bit further, to realign perfectly with the Earth and the sun.
Which recreates that exact full moon phase. That makes so much sense.
It does. That geometric lag is fundamental to how we experience lunar phases. But an even more profound mechanical quirk is tidal locking.
Oh, yeah. Which is a concept that often gets simplified into, like, the moon just spins at the exact same rate it orbits.
Yeah, people say that a lot. And while that is the outcome, the physical mechanism driving it is actually called a gravity gradient torque.
Gravity gradient torque, that sounds intense.
It is. See, when the moon was forming, it was spinning much faster. But Earth's massive gravity didn't pull on the moon uniformly.
It pulled harder on the side facing us.
Exactly. It pulled slightly harder on the side of the moon facing the Earth than on the far side.
Which, if I'm understanding right, physically stretched the solid body of the moon into this ever so slight oval shape, like a tidal bulge.
You got it. And as the early moon tried to spin, that physical rocky bulge was constantly being dragged backward by Earth's gravity.
Like a brake pad.
Yes. That gravitational friction acted as an immense braking force, sapping the moon's rotational kinetic energy over millions of years.
Until that bulge was permanently locked, pointing directly at Earth, a 1.1 spin-orbit resonance.
Which leads to a persistent misunderstanding that we really need to clear up before we go any further.
Oh, I know exactly what you're going to say, the dark side of the moon.
Yes. Because we are tidally locked, we only ever see the near side. And this has popularized the phrase, the dark side of the moon.
I constantly see this used in media to describe, like, a permanent region of freezing shadow. But mathematically, there is no permanently dark side.
None at all. As the moon orbits us, that far side receives the exact same amount of solar radiation as the near side.
Right. When we look up and see a completely dark new moon, the far side is experiencing a blazing, fully illuminated full moon of its own. It is simply the far side.
The distinction is vital because as we dive into the data from the early space probes later, the geology of that far side is wildly different.
It really is. But the fact that we have such a massive satellite at all, I mean, one roughly a quarter the size of Earth, that's an anomalously large ratio, right?
Oh, absolutely. Compared to other planets in our solar system, it forces us to address a primary planetary physics problem. How did a body with that much mass end up trapped in our gravity well?
Because if you look at Venus or Mercury, they have absolutely nothing. Mars has 2 tiny captured asteroids.
Oh, we have a behemoth.
Exactly. And the journey to answering that brings us to the giant impact hypothesis.
But before we get into the modern consensus, I think it's worth looking at the older discarded theories. They really highlight just how difficult this was to solve dynamically.
Yeah, for a long time, the scientific community was deeply fractured on this. You had the fission theory, proposed in the late 19th century by George Darwin.
Charles Darwin's son, actually.
Really? I didn't know that. Well, he suggested the molten early Earth was spinning so incredibly fast that centrifugal force overcame gravity.
Right, and a massive chunk of the Pacific Basin essentially detached and was flung into orbit.
But the fluid dynamics of the fission theory ultimately collapsed under scrutiny, didn't they?
They did. For Earth to eject a mass the size of the moon, its rotational period would have had to be less than 2 hours.
Wow. 2 hours.
Yeah. A planet spinning that fast would likely obliterate itself entirely, tearing apart at the equator before a clean fission event could ever occur.
So the angular momentum calculations simply could not be balanced.
Exactly. Then you have the capture theory.
Right, which argued the moon formed independently elsewhere in the solar system, perhaps out near Mars, and eventually wandered too close.
And got snagged by Earth's gravitational net.
But orbital mechanics makes this incredibly improbable, doesn't it?
Very much so. If a body that massive approaches Earth, it carries an enormous amount of kinetic energy.
Unless there is a third massive body nearby to bleed off that energy, or some impossibly dense atmospheric drag to slow it down, it just wouldn't work.
Right. The incoming moon would just accelerate into a hyperbolic trajectory and slingshot right back out into deep space. You can't just catch a fast-moving object of that size.
You'd need a massive braking mechanism, which leaves the co-formation theory.
The idea that Earth and the moon accreted side by side from the same localized swirl of primordial dust and gas.
But that model fails a basic geophysical test, right?
It does. If they formed from the exact same local material pool, they should have roughly the same bulk composition.
And they don't. Earth is a dense, metallic-hearted planet. Our iron core makes up about 32% of our total planetary mass.
The moon, however, has an anemic iron core, comprising only 1 to 2% of its mass.
So if they form together from the same dust cloud, the moon should be just as iron-rich as Earth.
Exactly. Those structural failures in the old models paved the way for the giant impact hypothesis.
Which paints an almost unthinkably violent picture of the early solar system.
It really does. We are looking at a time frame around 4.5 billion years ago, just tens of millions of years after the solar nebula collapsed.
The solar system wasn't the orderly clockwork we see today, right? It was a chaotic shooting gallery of migrating protoplanets.
A cosmic shooting gallery. The model proposes that the proto-Earth was struck by a Mars-sized rogue planet.
A protoplanet given the moniker Theia, named after the Greek titan who birthed the moon goddess Selene, which is super fitting.
It is aptly named, and Theia's trajectory was absolutely critical here.
Because if it had been a direct center mass impact, the combined kinetic energy would have likely shattered both bodies, right?
Creating an asteroid belt instead of a planet, but the physics point to a glancing blow, an off-center strike.
It basically played a massive cosmic game of billiards, taking a high-speed corner pocket shot at Earth.
That's a great way to visualize it. And the sheer thermodynamics of that event are staggering.
I mean, the kinetic energy of two planetary bodies colliding at tens of thousands of miles per hour, it would instantly convert into thermal energy,
Absolutely. The impact would have liquefied the mantles of both worlds.
flinging billions of tons of vaporized rock, superheated plasma, and magma out into space, creating this massive debris ring around the Earth.
And that glancing impact elegantly resolves the angular momentum problem that plagued the older theories.
Oh, because the Earth-Moon system possesses an unusually high angular momentum compared to other terrestrial planets.
Right. That off-center strike from Theia imparted a massive rotational spin to the Earth, acting as the energetic catalyst for the entire system.
And it perfectly explains the iron core deficit too, doesn't it?
It does. When Theia slammed into Earth, its dense iron core surrendered its momentum and plunged deep into the molten Earth.
Eventually merging with our own core.
Meanwhile, the lighter, iron-poor silicate material from the outer crusts and mantles of both bodies was blasted into orbit.
That material coalesced to form the Moon, which is why it is essentially a world made of crust and mantle rock just starving for iron.
Exactly. Now, the prevailing assumption used to be that this debris ring cooled and clumped together over centuries, or maybe millennia.
But the 2022 high-resolution supercomputer simulations from NASA threw a massive wrench into that timeline.
They really did. Using smooth particle hydrodynamics, the math suggests we weren't looking at a slow accretion at all.
The simulations showed the ejecta splashing out past the Roche limit, right? The distance where Earth's tidal forces would shred any forming body.
Right, and it coalesced into the Moon in a matter of hours.
Wait, hours, not decades or centuries.
Literally just hours.
Yeah.
The computational fluid dynamics involved in those 2022 simulations are breathtaking.
I can only imagine. They modeled millions of individual particles interacting gravitationally and thermodynamically.
Yeah, you see this violent shear, a spiral arm of molten rock extending from Earth. And almost immediately, gravitational instability causes the tip to collapse into a cohesive sphere.
A satellite born in a single afternoon. It is a beautifully brutal, elegant theory.
It is. But as we move forward with lunar exploration, specifically the Apollo data, scientists hit a massive wall.
Yeah, the exact same wall they hit in the late 1990s. The giant impact theory had a massive glaring contradiction.
A chemical fingerprint that didn't just complicate the model, it threatened to break the physics of the impact entirely.
You were referring to the isotopic crisis.
Yes, the isotopic crisis. Between 1969 and 1972, the Apollo program achieved the impossible, returning 842 pounds of lunar rocks and regolith to Earth.
And geochemists were eager to analyze these samples because they assumed the rocks would act as a forensic smoking gun.
Exactly. According to the giant impact models at the time, the vast majority of the material that was blasted into orbit to form the Moon came from Theia, not Earth.
So, logically, if you analyze a moon rock, you are looking at the alien geology of Theia.
Right. And scientists measure this using stable isotopes, specifically oxygen isotopes.
Let's break that down for a second. Oxygen comes in different masses, like oxygen-16, which has 8 protons and 8 neutrons, and heavier oxygen-18.
Yes, and the ratio of these isotopes acts as a highly specific planetary DNA signature.
Because Mars has a specific ratio, meteorites from the asteroid belt have a different ratio.
Exactly. Because these bodies formed in different temperature zones of the solar nebula, their oxygen isotopes fractionated differently.
So the expectation was that the Moon, being mostly composed of Theia, would have an isotopic signature wildly different from Earth's.
But when the mass spectrometers output the data, the results were paralyzing.
The stable isotope ratios for oxygen, titanium, chromium, and tungsten, they were virtually identical.
Identical. The Earth and the Moon were not just similar. They were perfect chemical twins down to parts per million.
Which makes zero sense under the standard impact model.
None whatsoever.
I mean, if a random rogue planet hits us, the statistical probability of it having the exact same isotopic DNA as Earth prior to the collision is vanishingly small.
Calculated at less than 1%.
It's literally like getting a DNA test for your newly adopted child and finding out they are your exact biological clone. How is that possible if they came from another planet?
What's fascinating here is how the scientific community scrambled to reconcile this paradox. The isotopic crisis forced researchers to completely reimagine planetary collisions.
One early attempt was the equilibration hypothesis, right?
Yes. This proposed that in the immediate aftermath of the impact, the molten Earth and the swirling protolunar disk were enclosed in a shared massive atmosphere of vaporized silicate rock.
And for roughly a century, these two bodies essentially cooked together, exchanging volatile elements.
Right, homogenizing their chemical signatures through violent convection before finally cooling and separating.
So they basically stirred their elemental ingredients into a single uniform batch.
Exactly, but even that felt like it required a very specific, almost delicate balance of temperatures to work without the atmosphere just boiling away into the vacuum.
Which led to the development of a much more extreme model, the synestia model. And the physics behind a synestia sound like absolute science fiction.
They really do. The synestia model discards the idea of a neat, solid planet being struck by another solid planet.
It argues that the impact was so insanely energetic that it literally vaporized the entire proto-Earth and Theia.
Yes, the collision injected so much angular momentum and thermal energy that Earth expanded beyond its own rotation limit.
The equator was spinning faster than orbital velocity.
Exactly. The planet transformed into a massive, rapidly rotating, donut-shaped torus of vaporized rock and superheated plasma.
A spinning torus of vaporized planetary guts. That is wild.
It is. And inside this chaotic, churning plasma donut, temperatures and pressures were so extreme that all the chemical elements from Earth and Theia completely vaporized and mixed.
Then, as the synestia began to radiate heat into space and cool, droplets of magma began to condense and fall like molten rain.
And the moon seeded and formed inside this outer cloud of homogeneous vapor.
So once the system cooled enough, the remaining vapor collapsed back into a sphere to form the Earth, leaving the moon in orbit.
Precisely. Both formed from the exact same vapor pool, perfectly explaining why their isotopic DNA matches.
It is a profound shift in how we view state changes in planetary masses.
It is. But the science hasn't stopped there. The stack of sources we are synthesizing brings us right to the bleeding edge of current research.
Yeah, specifically studies published in late 2025 and early 2026, which are aggressively rewriting these models yet again.
A landmark paper published in Science in November 2025 by researchers from the Max Planck Institute and the University of Chicago tackled the isotopic problem from a new angle.
Iron isotopes, right. I was poring over that Max Planck study, and their precision is unbelievable.
Well, it's incredible. They weren't looking at the bulk iron. They were measuring minute variations in heavy iron isotopes.
And what they deduced completely reframes who Theia actually was. We used to picture Theia as this exotic intruder.
Right. Perhaps a rogue planet that formed way out near Jupiter, got gravitationally kicked inward and slammed into us.
But the iron isotopic signatures forbid that origin story.
They absolutely do. By analyzing the specific ratios of iron 56 to iron 54 in lunar samples and comparing them to terrestrial and chondritic meteorite baselines, they proved that Theia was not a migrant from the outer solar system.
So the isotopic fractionation indicates Theia was formed in the inner solar system.
Yes, the calculations strongly suggest Theia accreted even closer to the sun than Earth did, baking in a highly irradiated environment before migrating slightly outward into an intersecting orbit.
So Earth and Theia weren't strangers at all. They were localized planetary neighbors formed from the exact same regional batch of solar nebula material.
Which deeply contextualizes why their isotopic signatures were so similar even before the collision.
But just as that piece of the puzzle slides perfectly into place, I see a Brown University study from early 2026 that introduces a completely new wrinkle.
Ah, yes. Regarding lunar soils and an isotope called sulfur-33, the Brown University findings are highly disruptive.
Because sulfur is a volatile element, meaning it vaporizes at relatively low temperatures.
Right. And in the extreme heat of the giant impact, or a synestia, models predict that certain mass-dependent fractionation should occur as sulfur boils away.
But the researchers found a highly anomalous depletion of the specific isotope sulfur-33 in the lunar regolith.
And that depletion does not align with standard evaporative loss models in a vacuum.
Right, because if the sulfur just boiled off into the vacuum of space, it would fractionate at a predictable mathematical rate based on mass.
Exactly. But this specific depletion pattern requires an entirely different mechanism.
The study posits that the early moon didn't just solidify in a vacuum. It suggests the moon possessed a transient, dense atmosphere of vaporized metals and sulfur.
And ultraviolet radiation from the young sun was photochemically reacting with this sulfur atmosphere,
Preferentially stripping away the sulfur-33 before the entire atmosphere ultimately boiled off.
The implication is profound. It suggests the early moon wasn't just a glowing ball of magma.
It was a complex, dynamic system with a transient meteorological cycle of metal silicate vapor,
driven by intense solar radiation, rapidly altering the surface chemistry of the crust as it cooled.
This realization that Theia didn't just bump into us, but absolutely annihilated the old Earth, vaporized it, and forced a complete chemical reboot, is pivotal.
It really is the foundation of our entire planetary history.
Because Thea's sacrifice didn't just leave a sterile rock in our orbit. The mechanics of that impact and the massive gravitational anchor it left behind fundamentally rewired Earth.
It turned a chaotic, spinning molten blob into a highly regulated cradle for life.
If we connect this to the bigger picture, the moon is arguably the most critical external component of Earth's biological life support system.
Without a doubt, we can analyze its influence through three massive planetary shifts, starting with obliquity or axial tilt.
Right, because Earth doesn't sit perfectly vertical relative to its orbital plane around the sun. We are tilted at roughly 23.5 degrees.
And the gravitational pulls from the gas giants, particularly Jupiter and Saturn, are constantly tugging at Earth, trying to perturb that tilt.
If you run the Milankovitch cycle models on an Earth without a massive moon, the math gets apocalyptic fast.
Very fast. Without the immense stabilizing torque provided by the moon's gravity, Earth's rotational axis would be highly susceptible to those planetary perturbations.
Like training wheels for a wobbly bicycle.
Exactly. Over millions of years, Earth's tilt could chaotically swing anywhere from 0 degrees to 60 or perhaps even 90 degrees.
And the resulting climate shifts would be catastrophic for the evolution of complex terrestrial life. Imagine the thermal dynamics of an 85-degree tilt.
It means the planet is essentially knocked on its side, rolling like a barrel around the sun.
For 6 months out of the year, the northern hemisphere would be pointing directly at the sun. The oceans would literally boil at the equator and the pole.
While the entire southern hemisphere sat in absolute freezing darkness.
And then 6 months later, it violently reverses.
You cannot sustain the slow, fragile evolution of multicellular life when the planet's climate aggressively sterilizes the continents every few million years.
The moon's gravity locks our tilt in place, ensuring the mild, predictable seasonal variations that allow biomes to stabilize.
The second massive planetary shift is the regulation of rotational kinetic energy.
Slowing time down.
Yes. Following the giant impact, the newly reformed Earth was spinning at a blistering rate.
The conservation of angular momentum from that collision gave the early Earth a day that lasted only about 5 hours.
Try to picture the fluid dynamics of a planet spinning that fast.
The Coriolis effect, the force that drives weather patterns and hurricanes based on the planet's rotation, would have been violently amplified.
A 5-hour rotation period would generate continuous planet-wide superhurricanes.
The atmospheric shear would constantly scour the barren land masses. It sounds terrifying.
It does. But over the past 4 billion years, the moon has been systematically bleeding off that rotational energy through the mechanism of tidal friction.
Because Earth's oceans are pulled by the moon's gravity into a tidal bulge.
And because the Earth rotates faster than the moon orbits, the Earth is constantly dragging that massive wall of water ahead of the moon.
The physical friction of billions of tons of water scraping across the shallow continental shelves generates immense drag, doesn't it?
Exactly. The moon's gravity pulls backward on that leading water bulge, literally applying a brake to the Earth's solid crust.
So this kinetic energy is transferred outward, converting into orbital potential energy for the moon.
As the Earth slows down, stretching our incredibly fast 5-hour day to the 24 hours we experience now, the moon is simultaneously pushed into a higher orbit.
It is slowly spiraling away from us at a rate of roughly 1.5 inches per year. We are constantly trading our spin for the moon's distance.
And that brings us to the third mechanical shift, which is perhaps the most biologically vital: tides and life.
Because early on, the moon was exponentially closer to the Earth in the Hadean and Archean eons, so the gravitational gradient was far steeper.
The tidal forces follow an inverse cube law regarding distance, meaning even a small decrease in distance results in vastly larger tides.
So the early oceans weren't experiencing the gentle 6-foot coastal swells we see today.
Not at all. We were talking about colossal, terrifying walls of water, potentially hundreds of feet high, sweeping miles inland every few hours.
But that violence was chemically necessary, right? The early continents were just barren rock, completely devoid of organic soil.
Those megatides acted like a planetary grinding mill. They violently eroded the continental shelves, scouring vital minerals, silicates, and metallic nutrients from the rock.
And dragging them back into the oceans. This relentless mechanical weathering created highly enriched, nutrient-dense tidal pools along the coasts.
From a biochemical perspective, those isolated tidal pools provided the perfect concentration gradients and thermodynamic environments for early organic chemistry.
They acted as the chemical mixing bowls, where simple amino acids could polymerize into the first complex proteins and RNA strands.
Furthermore, the constant churning of those massive tides forced the circulation of deep ocean currents.
Preventing the oceans from becoming stagnant, toxic pools. Even today, lunar-driven tides regulate global marine ecosystems.
By circulating nutrients and oxygenating the water column, it's an incredible chain of causality.
Without the giant impact, we would have chaotic boiling seasons, atmospheric superhurricanes, and chemically stagnant oceans.
The biological heartbeat of our planet is paced by lunar gravity.
And because the moon's physical rhythms were so deeply hardwired into the Earth's environment, it is entirely logical that when humans evolved, the moon became the foundational anchor of our culture.
It absolutely became the birthplace of ancient science. We can trace the epistemology of timekeeping directly to lunar mechanics.
Right, for ancient Paleolithic hunter-gatherer societies, understanding the passage of time was an absolute survival prerequisite.
But tracking the solar year is difficult without fixed architectural observatories. The slow drift of the sun along the horizon is subtle.
The moon, however, provides a visceral, highly visible, and perfectly reliable 29.5-day synodic cycle.
It changes shape, changes position, vanishes into the new moon, and reliably resurrects itself.
I look at anthropological artifacts like the Ishango bone from Central Africa, which is over 20,000 years old.
The tally marks carved into it strongly suggest early humans were tracking lunar phases.
This wasn't just abstract mathematics. It was the biological key to transitioning from nomadic survival to complex civilization.
You cannot invent agriculture if you don't have a reliable calendar to predict the spring thaw and the autumn frost.
And you can't coordinate massive hunting parties without a mutual understanding of when a specific month begins.
The moon provided humanity with its first standardized unit of measurement.
And this tracking embedded itself deeply into the linguistic and cultural DNA of our species.
The mythological reverence is obvious. The Greeks worshipped Selene and Artemis. The Romans revered Diana and Luna.
But the linguistic archaeology is even more telling. The English word moon itself is a linguistic fossil.
It is. It traces its roots all the way back to the Proto-Indo-European root word mahans,
which literally translates to month, deriving from the verb meaning to measure time.
We fundamentally viewed the moon not just as an object, but as the cosmic ruler by which we measured our own existence.
The shift from viewing the moon as a celestial deity to an object of physical measurement represents the dawn of the scientific revolution.
When Galileo turned his crude 20x magnification refracting telescope toward the moon in 1609, he didn't see a perfect, unblemished heavenly sphere.
Which was the prevailing Aristotelian dogma of the time.
Exactly. He saw mountains casting stark, jagged shadows. He saw deep, cratered valleys.
He realized the moon was a geological world governed by the same physical topography as Earth.
And that realization sparked a 350-year technological sprint that culminated in the space age.
Humanity went from tracking its phases with carved bones to strapping ourselves to 3,000-ton Saturn V rockets to go up there and touch it.
While more than 105 robotic spacecraft have visited the moon, the Apollo program remains the absolute pinnacle of lunar exploration.
Entirely because of the physical geology they brought back.
We mentioned the 842 pounds of samples earlier in the context of the isotopic crisis.
But the physical mineralogy of those rocks settled one of the most contentious debates in planetary science.
Before Apollo 11 landed, there were highly respected scientists who argued the moon had always been a cold, dead primordial rock that simply clumped together.
But the very first rocks Neil Armstrong and Buzz Aldrin picked up from the Sea of Tranquility were basalts and anorthosites.
When geologists examined the anorthosite samples back in Houston, they found they were composed almost entirely of plagioclase feldspar.
Now, the thermodynamics of crystallizing plagioclase feldspar requires a highly specific environment, doesn't it?
It does. It is a relatively light mineral. The only way you get a vast surface crust made of plagioclase is if the entire exterior of the moon was once a churning global ocean of liquid magma hundreds of miles deep.
The magma ocean theory. That became the bedrock of lunar geology.
As the violent heat from the giant impacts slowly dissipated, the global magma ocean began to cool and crystallize.
Dense iron and magnesium-rich minerals like olivines sank deep into the lunar interior to form the mantle.
Meanwhile, the lighter plagioclase feldspar crystallized and literally floated to the surface of the magma ocean.
Forming the bright, reflective primary crust we see today in the lunar highlands. It is planetary differentiation happening in real time.
And because those rocks crystallized from a melt, geochemists could finally lock in the absolute age of the moon.
By measuring the radioactive decay chains, specifically looking at how uranium decays into lead, they radiometrically dated those crystals.
The data pinpointed the moon's formation to a window roughly 60 to 175 million years after the birth of the solar system itself.
Here's where it gets really interesting, because the Apollo legacy extends far beyond the rocks themselves.
Yes, the astronauts deployed a suite of geophysical instruments, most notably the passive seismic experiment packages.
These seismometers operated until 1977, right? Beaming telemetry continuously back to Earth.
And the data they transmitted completely shattered the notion of a geologically static moon.
Because the seismometers detected thousands of moonquakes. But the moon lacks tectonic plates, so what is physically driving these deep moonquakes?
The primary mechanism is tidal stress. Even though the moon is tidally locked to Earth, its orbit is an ellipse, not a perfect circle.
As the moon moves slightly closer to Earth and slightly farther away, Earth's immense gravity physically stretches and squeezes the solid lunar sphere.
This constant rhythmic gravitational flexing builds up stress deep in the lunar mantle, roughly halfway to the core,
Causing deep fracture networks to snap and release seismic energy.
Furthermore, the moon is slowly shrinking as its deep interior continues to lose thermal energy, causing the brittle outer crust to buckle.
But the physics of how those seismic waves travel through the moon is totally alien compared to Earth.
Oh, completely. On Earth, the crust is saturated with oceans, groundwater, and pliable rock, which acts as a massive acoustic dampener.
So an earthquake fades away quickly, but the moon is bone dry. The crust is profoundly fractured from 4 billion years of continuous meteorite bombardment.
When a moonquake occurs, the seismic waves bounce chaotically through this dry, shattered rock without losing much energy.
As a result, the moon can literally ring and reverberate like a struck bell for over an hour.
It is a phenomenal demonstration of how water alters planetary geophysics.
But as we map the surface, a glaring morphological dichotomy became impossible to ignore. The anatomy of the moon is incredibly, inexplicably lopsided.
The near side, the face humanity has observed forever, possesses a geological composition fundamentally different from the far side.
When you look at the near side, you see these massive, dark, smooth regions.
Early astronomers looking through primitive telescopes thought they were vast oceans of water, which is why they named them Maria, the Latin word for seas.
We know now they are not water, they are sprawling plains of cooled basaltic lava.
Billions of years ago, enormous asteroid impacts cracked the thin, near-side crust, allowing highly fluid, iron-rich magma from the mantle to seep up.
And flood the impact basins, cooling into these dark, flat expanses.
The crust on the near side is surprisingly thin, averaging only about 43 miles in depth.
But when the Soviet probe beamed back the very first images of the far side in 1959, the scientific community was stunned.
The far side is almost entirely devoid of Maria. It is a hyper-cratered landscape of ancient highlands.
And later gravity mapping confirmed that the crust on the far side is massively thicker, averaging around 93 miles thick.
This crustal dichotomy presents a fascinating thermodynamic puzzle. Why would a global magma ocean cool unevenly?
I have to ask, why did this happen?
The leading mechanism ties directly back to the tidal locking we discussed earlier, combined with the extreme temperatures of the early Earth.
Right, following the giant impact, the Earth and the Moon were only about 15,000 miles apart.
And the Earth wasn't a cool blue marble. It was a seething ocean of magma, radiating thermal energy at temperatures exceeding 2,500 degrees Kelvin.
Because the Moon tidally locked very quickly, the near side was permanently locked into staring at this blindingly hot, massive planetary space heater.
The radiant heat from Earth blasted the near side, fundamentally altering its cooling rate.
While the far side was pointed outward toward the freezing absolute zero of deep space, allowing it to rapidly cool and crystallize a thick crust.
The near side was kept warm. The plagioclase crust couldn't thicken.
So later, when radioactive elements reheated the mantle, that magma easily punched through the thin near-side crust to form the Maria.
While the thick far side crust kept the magma trapped underground, it elegantly explains the visual asymmetry.
While the near-side-far side mystery is largely understood, the Apollo rocks brought back a paradox that haunted scientists for 50 years.
Literally remaining unsolved until early 2026.
The 50-year magnetic mystery. To understand the paradox, we need to look at how a planetary body generates a global magnetic field.
It requires a mechanism called a geodynamo. Inside Earth, you have a massive outer core of liquid iron.
As the inner core cools, it releases heat, causing the liquid iron above it to violently convect and boil upward.
Combined with the Coriolis force from Earth's rapid rotation, this generates electric currents, which produce our massive magnetic field.
But a dynamo requires volume, intense heat gradients, and a liquid conductor. The moon's iron core is tiny.
Perhaps only 200 miles in radius. A core that small will radiate its heat away rapidly.
Meaning the moon should be magnetically dead.
Yet when geophysicists ran magnetometers over the Apollo basalts, several of the rocks were highly magnetized.
Suggesting the moon had a powerful magnetic field for 500 million years. This broke our understanding of planetary physics.
How do you extract 500 million years of intense magnetic dynamo activity from a tiny core?
The theories proliferated for decades. Did massive asteroid impacts send shockwaves through the core? Did tidal locking create mechanical stirring?
None of the mathematical models could sustain a 500 million year field without violating thermodynamics.
But the breakthrough finally arrived in an exhaustive 2026 study published by geophysicists at Oxford University.
And the answer wasn't a failure of physics. It was an extreme case of gravitational and geological sampling bias.
The mechanism the Oxford team proposed is brilliant. To solve the magnetism, you have to look at how NASA chose its landing sites.
The Apollo lunar modules were incredibly fragile machines. Mission control required large, flat, hazard-free zones for landing.
Consequently, all the early missions intentionally targeted the lunar Maria, those dark, flat plains on the near side.
But from a geochemical perspective, those Maria are heavily concentrated within a specific geological province known as the Procellarum Creech terrain.
And that specific region is anomalously rich in a mineral called ilmenite, which is a dense titanium-bearing oxide.
When the lunar magma ocean was crystallizing, this heavy ilmenite formed late in the process, solidifying near the surface.
But because it was denser than the mantle rock beneath it, it created a massive gravitational instability, heavy rock floating on lighter rock.
Which triggers a fluid dynamics process called Rayleigh-Taylor instability.
Eventually, that dense titanium-rich ilmenite couldn't support its own weight, right?
Correct. It collapsed, triggering a global mantle overturn. Massive cold blobs of heavy titanium rock sank like stones through the hot mantle,
plunging hundreds of miles down until they violently collided with the boundary of the lunar core.
This is where the Oxford study unlocks the dynamo. When these cold blobs hit the hot core boundary, they created extreme, localized temperature differentials.
This massive thermal shock violently accelerated heat extraction from the core, forcing the liquid iron to rapidly convect.
This rapid convection sparked the geodynamo back to life, generating an intense magnetic field.
But the key to the paradox is the duration. These titanium-driven dynamo bursts weren't stable for 500 million years.
They were incredibly brief, violent, magnetic hiccups that only lasted a few thousand years.
An absolute blink of an eye in geological time. As soon as the temperature gradient neutralized, the dynamo died.
The bias occurred because NASA only sampled the exact regions where these titanium sinkers originated and eventually re-erupted as magma.
The Apollo basalts didn't record a continuous 500 million year field. They captured disparate, fleeting magnetic bursts.
The Oxford researchers offered a brilliant analogy. If aliens visited Earth and only landed in the Sahara Desert 6 times, they would assume Earth was a completely waterless planet.
Because NASA only sampled the Maria, we accidentally grabbed rocks from the exact rare moments the moon was magnetic.
It's a stunning reminder of the limitations of localized data.
And it perfectly frames why the current era of spaceflight is pivoting so aggressively. To prove this new theory, we have to go back.
Which brings us to the Artemis program and the renewed interest in the moon. We are officially entering a new golden age of lunar science.
Future missions are specifically targeting regions far from the Apollo sites, like the lunar South Pole.
The South Pole is scientifically vital. The moon's axis is only tilted about 1.5 degrees, meaning sunlight always hits the poles at an extreme horizontal angle.
This geometry creates deep craters at the poles whose floors haven't seen a single photon of sunlight in over 2 billion years.
These permanently shadowed craters drop to temperatures around 40 degrees Kelvin.
At those temperatures, water ice delivered by ancient comets and meteorites is trapped and preserved indefinitely.
From a logistical standpoint, mapping and extracting that ice provides drinking water and rocket propellant for a sustained human presence.
But from a pure geology perspective, Landing at the South Pole gives geochemists pristine highland crust material that has never been contaminated by the titanium-rich basalts.
By running magnetometers over these new samples, scientists can definitively prove the Oxford theory.
And extracting deep core samples from the South Pole Aitken Basin will provide the raw isotopic data to finally lock down the synestia model. You are living in a time where textbooks about the moon are actively being rewritten. Every time you look up, humans are closer to returning.
If we connect this to the bigger picture, the moon is the ultimate time capsule. Because it lacks weather and plate tectonics, it preserves the 4.5 billion-year-old history of our violent solar system in pristine condition. It is a mirror reflecting our own missing planetary history.
Think about the absolute razor-thin cosmic luck required for this to happen. If Theia had hit us slightly more head-on, Earth would have been destroyed. If it missed, Earth would spin wildly out of control, seasons would be chaotic, and complex life might never have evolved. When you look at the moon tonight, don't just see a rock in the sky. See the very reason you are here, breathing, and able to look up at it at all. Thank you for exploring this with me on GL Deep Dives. If you enjoyed the episode, make sure to follow and subscribe because even the closest things still have secrets left to uncover.